Okay, I'll tell him. Hola, buenas noches, bienvenidos a la Ciutat de les Arts y les Ciències. Esta noche tenemos a Pedro Ferreira, que viene de la Universidad de Oxford, es astrofísico y viene de la mano del British Council. El British Council, la institución que tenemos un convenio de colaboración con el British Council y la Ciudad de las Artes y las Ciencias desde hace muchos años y siempre traen muchos ponentes de mucho prestigio, como muchos de vosotros que veo habréis comprobado. Y esta tarde tenemos a Anne Fairfield, que es la actual directora del British Council Valencia. Ella os va a hacer una pequeña presentación de nuestro prestigioso ponente. Cuando quieras, Anne. Gracias.
Hola, buenas tardes a todos y muchas gracias por venir. Como ha dicho Araceli, nuestro ponente de hoy es Pedro Ferreira, de la Universidad de Oxford. Anteriormente, Pedro ha trabajado como investigador en la Universidad de California en Berkeley y en el CERN en Ginebra. Sus áreas de especialización son la cosmología, el universo temprano y la teoría general de la relatividad de Einstein. Pedro ha sido uno de los pioneros en la investigación tanto de los vestigios de la radiación del Big Bang como de la naturaleza del universo oscuro. También se dedica a la divulgación de la ciencia y colabora con publicaciones tan prestigiosas como Nature, Science, New Scientist o The Guardian. Su libro más reciente, La teoría perfecta, editada en España por Anagrama y en el que se basa la charla de hoy, ha sido publicado en más de 20 países y fue seleccionado para el Royal Society Winton Science Prize, el premio más prestigioso del Reino Unido concedido a libros científicos. Doy las gracias a Pedro por estar esta tarde con nosotros y sin más le cedo la palabra. Muchas gracias.
I would love to speak in Spanish. I'm originally from Portugal, so I could speak Portuñol, but I'm not going to. I'll speak in English. I'm very happy to be here. I wandered around Valencia today, and one of the things that just comes back to me again and again is how Spain has these incredible cities and has so many of them. So it's a real pleasure to be here. I want to think back to 2016, February of 2016. In February 2016, I organized a meeting in one of the auditoriums at my university in Oxford. And it was an afternoon, and the idea is that we would sit and watch a live stream of a press conference by the National Science Foundation, by the American National Science Foundation. And this live stream was of a group of scientists and administrators announcing the discovery by an instrument, an observatory called, and I better get the name right, the Laser Interferometer Gravitational Wave Observatory, known as LIGO. And these people sat on the stage, and it was a half-hour presentation, and they announced that for the first time they had discovered gravitational waves. That is, ripples in space and time. Not only that, they discovered gravitational waves, and these were gravitational waves that arose from the collision of two black holes. Now, when they announced their results, I was in this room, the room was packed, and there was a collective chill. We were incredibly excited. I would say more, we were moved. Some of us were feeling quite emotional at that time. And why was this? Well, it was the first time in 100 years that we had been able to measure gravitational waves, one of the predictions of Einstein's theory of general relativity. Also, It was the fact that we had seen these two very esoteric objects, very strange objects, black holes, coming together and forming one. We were sitting in this room and we had a sense that history was being made before our eyes. The announcement was clearly Nobel Prize-winning science, so much so that the next year, the three designers, originators, conceptualizers of LIGO won the Nobel Prize. Now, I had heard of these results weeks before, even though the announcement was on that day. I had heard of these results weeks before, because there were rumors going around. People would come and visit me, I would send emails to people, and everyone knew more or less that LIGO was about to announce this discovery. And more, that this discovery was tied to these big black holes coming together. There was, in some sense, a kind of scientific gossip going on. There were things on Facebook, on Twitter. For old people like me, it was mostly through email. But it was definitely, there was a buzz in the air. Now, my girlfriend was a bit annoyed because I have a lot of children. And I was spending a lot of time looking at my phone instead of looking at my children. And she's an anthropologist. She's a social anthropologist. And she was saying, I really don't understand. I don't understand. Why are you so excited? Why are you so excited? You didn't invent this theory, and you're not making the discovery. So what is it that is making you behave like this? And it's an interesting question. And first there's the general answer. And the general answer is, when there is a discovery in science, you feel, there's a collective feeling that you can move forward. And you move forward to something, to the next step. And often this next step is into the unknown. So these discoveries, these scientific discoveries, open up this new path into the wilderness, into the unknown. And that's tremendously exciting. But there is more than that. There is the fact that this was a discovery tied to Einstein's general theory of relativity. And I've realized over decades that people who work or people who have any connection with this theory are completely obsessed with it. It's a personal obsession. It's almost like a religious cult. You really, you love it dearly, and you want things to work out. And so those were the two reasons that I could come up with to explain it to her. Now, in 2014, I published a book. And I published a book called The Perfect Theory, which is the title of this talk. And it was in some sense an attempt to bring together my ideas or my sense of why this theory is what it is, why it has the impact, the cultural impact, and what is the reason that people love it so much. And there were many ways that I tried to go about doing this. It's clear that I wanted to understand the phenomenon, and I couldn't just write a history of science book in the usual way. I needed to come up with a different way of doing this. And so I realized that I needed to, is this just a history of science? Well, that wouldn't be enough. Is it like a history of a political movement? In my youth, I was an active Trotskyite, and I cherished my youth, and I remember the passion with which we clung to our beliefs. Was it like a political movement? Actually, was it more like a cultural, artistic movement, like being a Dadaist or a Surrealist or in music a Serialist, where you're passionately committed to these rules and you really believe that this is the way to do things? And what I realized was actually, it's more like a person, that you have to look at this theory of general relativity, like a person. And that what I wanted to do, and what I ended up doing, was write a biography of this theory. Or to put it another way, again, a way that I could talk to my girlfriend about it was, it's like doing an ethnography. I wanted to do an ethnography where the subject is this theory. And so I'm going to try and give you a sense of the arc in this talk of why I think of looking at this theory in this way. Now, I haven't told you what this theory is. And to tell you what this theory is, I need to tell you what this theory is about. At the beginning of the 20th century, there were basically there are many, but there were two branches of physics that didn't quite come together. On the one hand, there was Newtonian mechanics, Newtonian physics, invented by Isaac Newton. It basically told us how things moved. Not only did it tell us how things moved, it told us how gravity works. There is this force, at the time people thought there was this force in the universe where if something has a mass, they attract each other. And you look out at the cosmos and you see planets orbiting the sun, you see planets orbiting planets. They're pulled together by this invisible magical force. Newton came up with a theory for this force. He came up with what is known as the law of universal attraction, where these objects are basically attracted. The bigger they are, the stronger the force. The further away they are, the weaker the force. But not only that, the way that this force communicates is instantaneous. If you move this a little bit, this body feels that automatically, instantaneous. So that's the Newtonian physics. On the other side, there was the physics of light, electricity, and magnetism, which was basically invented or discovered by Maxwell. And there, one of the essential elements of all of this is the propagation of light. And light propagates at a certain speed, and nothing can propagate faster than that speed. And this had led to an incredibly technological developments. It was well understood, but it clearly didn't match with Newtonian physics. With Newtonian physics, you had this instantaneous force, while with Maxwell, you had a finite speed limit. In 1905, Einstein was able to kind of connect certain things. He was able to connect part of Newtonian physics with Maxwell's theory. But in 1907, he decided that he needed to try and understand how to reconcile gravity with the fact that there was a maximum speed at which things could communicate. And over the next 8 years, he worked on his theory, and it was a trek through the wilderness. He got lost many times. He found it incredibly difficult. At some point, he realized that he needed to learn a completely new mathematics. He went to his friend, Marcel Grossmann, and asked him, can you help me with this? I'm completely lost. I'm going to kill myself if I can't figure this out. Marcel Grossmann said, go and learn something called Riemannian geometry. So Einstein turned to these math papers and books and learned it, and after a few years, he came up with his theory. In 1915, he came up with his theory of general relativity. And let me just be clear, this is a bit like us learning Sanskrit or Kimbundu or one of these languages and writing a novel from scratch. So it's a really remarkable feat. Now, I still haven't told you what general relativity is. I've told you what general relativity is about, but I haven't told you what it is. The idea behind general relativity is that space and time aren't anymore this static thing where you just put things and you see where they are and you wait for them to evolve. Space and time gain a life of their own. Space and time is very much an object in the way that this speaker is or the moon is. And let me give you an idea how it works. Imagine that you have space and time, and you put the sun in space and time. What the sun will do is it'll deform space and time. Space and time will change, it'll curve, it'll become different around the sun. Now, imagine that then you throw the earth through this space and time. As it moves through space and time, it'll feel that the space and time is deformed, it's changed, and it'll curve, and it'll curve, and it'll curve in such a way that it goes around the sun. So if you step back and you didn't know what space and time were doing, you would think that the earth was being pulled around the sun. But that's not what's happening. What's happened is that the sun has deformed space and time are acting on the earth, is acting on the earth. Now, these are all that's basically the general theory of relativity. It's this idea that the geometry of space and time interacts with energy, with things. Now, this can be just an interpretation. I gave you a description of the sun and the earth moving around, and you can say, well, it's just a reinterpretation of what's going on. But the fact is, there are physical consequences to this. There are real physical consequences. And one of the consequences that Einstein pointed out was, well, if you have an object that you put in space and time, and then you shoot a light ray, the light ray will curve around the object. It'll be like a lens. This object will sit there, will deform space and time, and the light rays will focus and come round. And so he proposed, look up at the sky, look at distant stars, and watch what happens to their light if a big object is put in front. And specifically, he said, well, why don't we look at distant stars, stars behind the sun? If we look at stars behind the sun, we measure their positions, and then we wait for the sun to be in front, and we measure their positions, and we should see them move together. Now, the problem with this experiment is that the sun is very bright, so you won't be able to see the stars when the sun is in front. So you need an additional thing. You need something to mask the sun, an eclipse. So what he said was, look at the positions of the stars, then wait for the sun to be in front and there to be an eclipse to mask the sun, and then look at the positions of the stars. An English astronomer, Arthur Eddington from Cambridge, decided to take up this challenge. And in 2019, i.e. 100 years ago, traveled to the small island of Príncipe in the Gulf of Guinea, near Gabon and Nigeria, well, what is now Gabon and Nigeria, and he measured. He knew there was going to be an eclipse on the 29th of May, 2019, and so he set up his apparatus and he measured. He measured the positions of some stars behind it. And he took a measurement of the stars before this, when there was no sun in front, and he found indeed that the stars shifted. He found indeed that, as Einstein had predicted, the stars moved their positions when the sun was in front. He announced his results in November at the Royal Astronomical Society and the Royal Society, and Einstein's theory was set. The press at the time, in the London Times and the New York Times, it made it to the front page. The announcement of this result made it to the front page. In the Times, you had titles like, all light askew, that means crooked, in the heavens. Stars not where they seemed or were calculated to be, but nobody need worry. Einstein became a superstar. And in an interview, again to the Times, he said, in Germany, I am called a German man of science, and in England, I am represented as a Swiss Jew. If I was wrong, if I come to be wrong about my theory, the description will be reversed, and I shall become a Swiss Jew to the Germans and a German scientist to the English. Now, I studied engineering in Lisbon. I studied engineering in this, if you've been to Lisbon, a little bit up from the center, there's this big institute, the Technical Institute, fantastic fascist architecture, this big building of steel, stone, and glass. And I was bored to tears by what I was learning. I was learning how to build bridges and electronics, all these things which I really wasn't that interested in. But I had one lecturer who told me, go and read Einstein's papers. They're really interesting. And I was amazed at how clean they were and how simple they were. And one of the things I realized at some point is that I wanted to learn this general theory of relativity. So I went to the library and I found all these books by incredibly eminent physicists, all whom had been seduced by Einstein's theory of general relativity. And I took these books down and I sat down and I studied it. And very much like Einstein, it was a trek through the wilderness. I began with not having a clue what it all meant. I taught myself this strange mathematics, and then at some point I understood it. And not only did I understand it, I could work out all these things that could be worked out with general relativity. For years I taught a course in Oxford on general relativity, and I saw it with my students. I started off and they didn't have a clue what was going on. They were completely lost, and by the end they had done it. They had worked out how to do things with general relativity. And this is very much what happened with general relativity. General relativity, the general theory of relativity, took on a life of its own. It became this thing that just grew and grew. And as one of my PhD students said, when you come up with a new theory, there is this phase where everything is easy, because all the easy calculations are there to be done. And this is what happened for the first 20 years. So, for example, there was a German astronomer based in Berlin who, this was 1916, he's actually fighting in the war, First World War. He's fighting on the front, on the Russian front, and he receives Einstein's paper on his general theory of relativity. He looks at it and he realizes that he can calculate something, and he calculates the space-time of a sun, of an object sitting in the middle of space-time. What is the geometry? How is space and time deformed around it? And he works it out, and he gets exactly what you expect. If you're very far away, it's as Newton predicts, but if it's close by, it's kind of strange. He sends his paper to Einstein, and he sends a letter to Einstein in which he says, "As you see, the war is kindly disposed towards me, allowing me, despite gunfire, at terrestrial distance, to take this walk in your land of ideas." Einstein receives this paper. He presents this paper to the Prussian Academy of Sciences. He doesn't really believe what's going on in the center, and he thinks there's got to be something wrong. But nevertheless, it's a step forward. A Soviet meteorologist in St. Petersburg and a Belgian priest in Leuven sit down, get hold of Einstein, independently get hold of Einstein's theory, and try to work out what happens not locally, but what happens to the whole universe. What does the whole of space-time do? And what they find is that the whole of space-time, they can solve it, and the whole of space-time evolves. It's not this static thing. It evolves. It expands. The universe has to expand. Now, Lemaitre, the Belgian priest, meets Einstein in 1927 in a conference in Solvay and says, "Master, did you receive my paper?" And Einstein says, "Yes, I read your paper." And he says, "Although your calculations are correct, your physics is abominable." Again, Einstein didn't really believe the prediction of his theory. Now, we now know that 3 years later, 2-3 years later, astronomers observed distant galaxies moving away from us and were able to show that the universe was expanding. So, yet another prediction from Einstein's theory. And so after these 10 years, there's these people doing the easy calculations, other people confirming some things with observations. But after 10 years, something very strange happens. Basically, paraphrasing the author Chinua Achebe, things fall apart. And the general theory of relativity dies a death. And there are many reasons for this. First of all, Einstein was not the best advocate of his theory. He seemed to react negatively to a lot of the predictions that his theory was giving, a lot of these fascinating predictions. That's the first thing. The second thing is, it was still a difficult theory to work with because you needed to learn this mathematics, this Riemannian geometry. And not a lot of physicists really wanted to do that. So it was still an elite group of people who could work with it, not everybody. But then there were other things. For example, in 1927, a completely different group of physicists discovered what is now known as quantum physics. Quantum physics is the physics that describes what happens on very small scales, explains atoms and molecules or even smaller scales. And it's a beautiful, complicated theory, but the great thing about it is that you can work on it, and you can tell someone in a laboratory to go and test your ideas. So in other words, it's very easy to test ideas with quantum physics. This isn't true with general relativity. So quantum physics basically sucked up the community of physicists, and then attention was focused on that. And people didn't really go into general relativity. But there were other aspects to this theory that made it difficult. Other aspects to history that made it difficult for this theory. For the for a start, in Germany, which was really the center of world physics, the rise of anti-Semitism took its toll. And in particular, the rise of a movement called Deutsche Physik decided to target Jewish physicists in Germany and make it difficult for them. And of course, Einstein was the archetypal Jewish physicist. And so a group of fascist or Nazi physicists decided to make it their mission to show that everything that Einstein was saying was wrong. And this was too much. First of all, it made people's lives difficult. A lot of Jewish physicists fled Germany. Einstein himself went to the US. But it was also disheartening for other people to work on this theory. In the Soviet Union, there was a movement within the academic philosophers to go against this very idealistic physics developed by the theoretical physicists. The philosophers pushed for dialectic materialism. It was to do with revolution, empiricism, and what Einstein was doing was experiments of the mind, mathematics. It was too idealistic, too idealized for what was acceptable to academia. Even in the US, the rise of quantum mechanics really took its toll on general relativity because quantum mechanics was useful. And it was so useful that in 1945, the Americans dropped a bomb on Hiroshima and Nagasaki based on quantum mechanics. It was from quantum mechanics that led to this. And so, by the early 1950s, one of the editors of one of the main scientific periodicals was saying, I really don't want to publish papers in general relativity. Thank God he didn't get away with it. And so for 25 years, general relativity had a very difficult time. Richard Feynman, one of the great physicists of the 20th century, went to a small meeting held in 1957 to try and re-energize research in general relativity. And he said the following: there exists one serious difficulty to general relativity. One serious difficulty, and that is the lack of experiments. The best viewpoint is that there are experiments and calculate. In this field, we are not pushed by experiments, but pulled by imagination. And then, after 25 years, or 20 to 25 years of this death, this difficult period, things began to happen. For a start, the pragmatism of the American scientific industrial military complex was that maybe there's something useful we could do with general relativity. We haven't really exploited general relativity the way that we exploit quantum physics. And they thought maybe if we understood general relativity better, we could design new aeroplanes, new ways of transportation through space. Maybe we could harness anti-gravity. Of course, this was a nonsense, but the end result was that they decided to put in money into research in general relativity. So the US Air Force and airplane companies decided to give funding to the few people who were working on general relativity. So that was one thing. Another thing was, during the war, a new generation of radio engineers was created to design defense systems, radar technology for detecting missiles, for looking for submarines. And they became very good at this radio technology. After the war, they used this technology not to look for things on Earth, but to look up at the skies. And they built radio telescopes to look up at the skies. And they discovered that the universe, as you looked in the skies, it was full of incredibly powerful objects emitting radio waves. So powerful that it was clear that to try and understand them, you needed to use general relativity. And these things really started to energize the field. But the most important thing of all was some very charismatic people decided to work in the field. And there were three main people who did this. In Princeton, a man called John Archibald Wheeler, who had worked on the American bomb project, he'd worked on the H-bomb. At some point, he decided to try and understand explosions of stars, what happened when stars collapsed. And to do that, he realized that he needed to understand general relativity. And the way that he did it is, first of all, he proposed to teach a lecture course in general relativity in Princeton physics, which had never been done. The second thing was to recruit very clever young people to come and work with him and do research with him in this new field. And from 1955 onwards, he got these people and they started looking at all the fascinating consequences of general relativity. Interestingly, in the Soviet Union, another guy, a guy called Yakov Zeldovich, had also worked on the Soviet bomb project and H-bomb. He got bored, as he said, every now and then you need to change field. And he decided to change field and try and understand all these radio observations and the biggest, what do the biggest objects in the universe, how do they behave? And for that, he needed to understand general relativity. And there again, what he did was to train this army of very young scientists and get them to focus on this problem. In England, in Cambridge, a man called Dennis Sciama, who had been interested in the evolution of the universe, he also decided to recruit these young people to work with him. And these are people who you've heard of. One of the people was Stephen Hawking. Another person was Roger Penrose. Another person was Martin Rees. And all of these people who are in their 20s, in the late 1950s, early 1960s, were recruited to start thinking about general relativity. And the end result is that general relativity took off again, injected by this new blood and these new techniques and new funding. People started looking at general relativity again, and it entered what has been called by one of John Wheeler's students, Kip Thorne, the golden age of general relativity. For 15 years, amazing discoveries were made. For example, with regards to black holes. Black holes was this solution that the German astronomer had found when he was fighting in the First World War. People looked at those again and more carefully, and they realized that actually these things might really exist in nature. Not only that, Roger Penrose proved that they had to exist in nature. Roy Kerr understood that they had to rotate, that they had a life of their own. As they understood more and more about these black holes, people realized that, okay, how do we look for them? How do we look for them with telescopes? And it became clear that these black holes are these engines, energetic engines, which stir up stuff around them and emit lots of energy. And so they said, look for them in X-rays, very energetic particles. People started to see them with X-rays. They said, they're dark, you don't see them, but they affect other stars near them. You should see other stars moving around because they're close by. People looked for these stars and they found them wobbling. And over the 1960s, this circumstantial evidence for black holes started to grow and grow and grow. In 1967, a young astronomer, Jocelyn Bell Burnell, built a radio telescope and discovered these pulses in the sky, these very regular pulses in the sky. And they called them little green men because they could be aliens. But actually what she had discovered were neutron stars, very dense stars made of neutrons, which people had realized would be the babies, the embryos for black holes. So not only were we beginning to see circumstantial evidence for black holes, we were getting an idea of where they would come from, and that where they would come from, we were finding these objects. On a completely different front, people looking up at the sky, again with radio telescopes, realized that there was this relic light, this bath of light left over from the very beginning, and realized that they discovered further evidence that the universe was expanding, that if you went back in time, the universe was much hotter in the past and would have left this hot bath of light. And so over this period of 15 years, this huge excitement, this huge creative, fertile period, general relativity grew and grew and grew. It became a theory which was rich in maths, mathematics, in concepts and observations. Now, I entered the field just over a decade after all this. And it was a very exciting field. I remember a meeting in Lisbon where some of these the children of general relativity of that generation came to give lectures, and I was fascinated by the whole thing. And I very rapidly became hooked by it. I became addicted to this theory. But I also had a sense that it was a very risky thing to work on. In 91, I moved to England, to Imperial College, to do my PhD, and I wanted to work on the combination of general relativity with quantum physics, the marriage of these two big theories. And what I realized is that it was a graveyard. If you moved into that theory, if you moved to work as a student in that field, it was very unlikely that you would survive. You would end up leaving physics and not working on it. Luckily, I began working on cosmology, which worked well. But one of the things that I realized is even though general relativity had gone through this explosion, it was still a difficult topic to work on. And I still see some of the people who fell out, who are casualties from general relativity. I know a colleague of mine who, at the time, had worked on general relativity, and at some point he just had to leave, and he works in computing. He constructs these incredibly complicated data warehousing techniques for storing large amounts of data. But whenever I see him, he wants to ask me about general relativity. The fire is still there. Another person I ran into a few years ago, I was at a meeting, and I was introduced to this man called Tim Palmer, and he's an incredibly famous scientist in the UK working on simulation of climate and climate change, and he's done some of the great work on this. And he introduced himself to me, and I told him what I was doing, and he said, "Oh, I'm a relativist." And I said, "You're not a relativist, you work on climate change." And he said, "Nope, I was a student of Dennis Sciama. I worked on all this, I worked on general relativity, and I still love it very much." And so again, this person who's very famous, who has all these awards working in another field, still considers himself to be a relativist. Now, I think things are changing now. I think we're entering a new golden age. And let me go back to that press conference that I told you about LIGO, and let's just look back at that. I invited the leader of that experiment, a man called Ray Weiss, to visit me in Oxford about a year ago. About 2 years ago, shortly after the discovery. And he told me what it was like for him to build LIGO, to build this machine that detected the gravitational waves. He said he started in 1972. He was at MIT, and he started constructing, he had this idea, and he started constructing these prototypes for making these measurements. And he was basically totally ignored. MIT would give him no funding. He got some funding from other places, but it was his own project. So much so that at some point people told him, "You've got to work on something else, otherwise we will kick you out." So while he was developing his gravitational wave technology, he had to work on something else. It took him 20 years until 1991, when the National Science Foundation first gave him a solid block of money so that they could start building his experiment. 20 years. And MIT still looked at it as odd, strange stuff. And it took almost another 20 years, not exactly, but almost another 20 years actually, before they were able to switch on this machine. It took another 20 years before they were able to switch on LIGO and start taking observations. And it was still another 5 years before they finally made the measurement. And of course, they make this measurement, and it's groundbreaking. He wins the Nobel Prize, and I now receive regularly in my emails announcing hiring positions for working in the detection of gravitational waves. This field, which was completely impossible to work with, it was difficult to get funding, is now the field, one of the big fields in physics. So clearly things have changed. There's this energy again in the general theory of relativity. But not only that, other things are happening, and you should prepare yourselves, because over the next 6 months there's going to be an announcement. Something called the Event Horizon Telescope, which is a consortium of telescopes, is going to observe the center of our galaxy. And in doing so, it's going to make the first image of a black hole. We know black holes exist, but they're pinpricks in space-time. We'll be able to look at this black hole, we'll be able to look at the effect of this black hole around the surrounding material. If you remember the movie Interstellar, there is this image of a black hole where you have this ring of light around this dark shadow. That's what we're going to see. So for the first time ever, and prepare yourselves, we're going to see the first measurement or the first image of a black hole. But there's not only that. New missions are being developed which come online in the next 3 years to map out the whole of space-time. So there's a satellite mission which is funded by ESA, the European Space Agency, which will map out the positions of galaxies out to very far in the past. There's a huge camera being built in Chile called the Large Synoptic Survey Telescope, this huge telescope which will basically take pictures of the sky every night and build up this huge map of the universe. And there is a new immense radio telescope which is being built in South Africa and Australia called the Square Kilometre Array. And to finish, I just want to finish with a little reading from my book where I talk about the Square Kilometre Array. So in 2009, I went to Príncipe, where Eddington did his eclipse measurement for a celebration there. And it was very moving for me because as you know, Portugal has a colonial past. A lot of my family was born in Mozambique, Angola, and my grandmother was actually born in São Tomé and Príncipe. She's from there. So I was curious to see this small island where my grandmother had been born in 1908. And while I was there, they organized parties. And they organized a celebration. And so, throughout the day, so I'm on this island in Príncipe, and we're celebrating. It's the 29th of May, 2009. It's 90 years after the observation. And so we've had these celebrations, and that night, we handed out telescopes to the crowd and looked up at the stars. The sky was breathtaking, ready to offer up much more that would help us delve deeper into Einstein's theory. I thought of how, even now, Einstein's theory was driving us to look out into the cosmos on a grander scale. The new Príncipe might not be in the south of Africa or in the Australian desert, might now be in the south of Africa or in the Australian desert, and the new telescope would use the latest, most powerful technologies of the 21st century. While Eddington had used an optical telescope, something with a lens, an eyepiece, and a photographic plate, this new phase will rely on radio antennas and dishes. Radio has already given so much to general relativity, but this time it'll go much further than has ever been envisaged. The idea is to build a collection of tens of thousands of radio antennas scattered across hundreds and thousands of kilometers, known as the Square Kilometre Array, or SKA, because the total collecting area of all the antennas should add up to a square kilometre. It will take one, possibly two continents to support it. Some of the telescopes will lie out in the vastness of the Australian West, and others will be strewn through the southern Africa. The core of the beast will be laid out in the Karoo Desert, but a number of these dishes will be scattered through the continent in places like Namibia, Mozambique, Ghana, Kenya, and Madagascar. It'll be a truly continental African endeavor. And in the same way that Eddington used Príncipe to establish general relativity, the SKA would be the beast that could test Einstein's theory on cosmological scales with unprecedented precision. That night, as we celebrated Eddington's and Einstein's colossal achievements, I thought about how we are only at the beginning of what the theory of space-time is going to tell us about the universe. The 21st century is surely going to be the century of Einstein's general theory of relativity. And I feel fortunate to be living at a time when so many new things are waiting to be discovered. Almost 100 years after Einstein finally came up with his theory, something fantastic is going to happen. And I'll end there. Oh, you want me to sit? Yes.
Bueno, espero que hayan disfrutado con la fantástica charla que nos ha dado Pedro. Ahora vamos a pasar a un turno de preguntas. Si tienen alguna pregunta, levantan la mano y activan el micrófono que tienen en la mesa.
How do the black holes create those radio waves when they collide?
How do they create radio waves? So it's more that they create gravitational waves, okay? And so what they do is, as they're moving, they basically think of it like water. Think of it like water, and you're stirring your hand, okay? As you stir your hand, you'll create these waves that propagate outwards. That's what's happening. These black holes are orbiting and coming together, and they're stirring up space-time and creating these waves.
Thanks.
You're welcome. No?
¿Nadie más se anima?
Hello, good evening. I want to ask you why is it so difficult to detect gravitational waves that you need black holes and stars are not enough?
That's a really good question, and it's basically because of the strength of a way of thinking about it is, think of how strong gravity is compared to electromagnetism, for example. Okay? Think of you need a whole planet to keep you glued down to here. But you only need a little bit of stuff to keep you held up, right? So just if I'm standing on a sheet of steel above the earth, you just need that little sheet of steel to hold you up, and that's using electromagnetic force compared to the whole pull of the planet keeping you down. Now, think of what that means in terms of the strength of the gravitational field, of the gravitational force. It's very, very weak. So to detect it, you need a huge machine to detect it because it's just so weak. Even though it's very energetic, the Earth is very big. The coupling, the connection between everything and gravity is very, very weak. And that's why you need such a big instrument.
Thank you.
You're welcome.
Así, para gente más ignorante, ¿nos puede explicar lo que es una onda gravitacional, por favor?
Yes, of course. So, I told you that space and time have a life of their own, okay? Which means that you can deform it. You can deform space and time. And an easy way to think about this is think of a rubber sheet, a sheet of rubber, okay? Now, I gave you a description, which is what happens if you put a planet in space and time. It'll deform it. But another thing you can do is you can just knock space and time. You can just knock it and see what happens. What happens to a sheet of rubber is that it vibrates, okay? Space and time will do exactly the same thing. And so what you're seeing, these waves in space and time, are like the waves in the rubber sheet. It's exactly the same thing.
Hello?
Yes.
In what way gravitational waves can help to astronomy? Thank you.
So, the way that we look at the universe is we look at things, photons propagating towards us. We look at light propagating towards us. And one of the great revolutions in astronomy has been to be able to look at light in lots of different frequencies. For example, when we look at radio astronomy, we're looking at light in frequencies or wavelengths of a millimeter. When we're looking at optical, we're looking at light in frequencies of hundreds of angstroms. And you can do this over a large range of frequencies. Gravitational waves is yet another way of looking. It's not light now, but it's gravitational waves. It's these gravity waves. But it's a different set of wavelengths that you can look at. And so, for example, you can look at objects which you might not be able to see with light because there might be things in the way that don't let light pass, but gravitational waves will come through. So it's another way of looking at the universe, which allows you to see different things. For example, black holes. Simple black holes don't emit any light, but they emit gravitational waves, so the only way of seeing them is through gravitational waves.
Hello. If we find something faster than light, the theory is wrong? The theory is wrong?
If we find something faster than light, well, the way that the theory is constructed at the moment, at the heart of it is that there's locally a maximum speed. Now, we have to be careful because often people sometimes confuse what's going on. For example, in electromagnetism, with normal light, we know that we can send light rays through different media, through materials, and it looks like it's moving faster than the speed of light. It's not, but it looks like moving faster. So the first thing to establish is whether things are actually, that the thing that you measure, that you discovered, which was moving faster than the speed of light, is actually moving faster than the speed of light. But if there are things moving faster than the speed of light, we need to reconsider the theory.
Hola, buenas tardes. Hola.
Where should I look?
Sí.
There, okay.
Sí. ¿Podría utilizarse las ondas gravitacionales para ver la materia oscura? Muchas gracias.
That's a really good question. So, one of the interesting consequences of the discovery of gravitational waves was that they saw them from these two black holes coming together. And so over the last few years, there are a few people who have been saying, well, what if the dark matter are black holes like this one? Okay? Like these ones. And there are people who think it's a good idea, other people who don't think it's a good idea. It's a possibility. And this would be exactly a case of what you're saying, where the only way to really, well, there are ways to see it indirectly, but the only ways to see the dark matter directly would be through gravitational waves. So, yes, for some cases of dark matter, it would be through gravitational waves. Okay.
Hola.
Hi. Good evening.
Quería saber si las ondas gravitacionales, las últimas que se detectaron con la fusión de dos agujeros negros, si son únicas, es decir, si solo tienen una frecuencia o las seguimos viendo o se han visto solamente una vez.
Can you? No, the gravitational waves can be constantly emitted. So, for example, when you have when you have black holes coming together, They're basically producing gravitational waves continuously until they come together. And when they settle down to a black hole, it's over. But you have a continuous emission of gravitational waves. The frequency is pretty constant, except towards the end, the frequency goes up, and then it's over. So there are various mechanisms to produce gravitational waves pretty consistently.
Yes. I wanted to ask you whether after the first announcement of the LIGO project, whether the people working in this project have discovered or have detected other gravitational waves. And the second question is, what do you think is the next evolution in this project?
So, over the last 3 years, there have been now, I think there are now over 10 detections of, and there's a table of all, and they're always black holes, which are quite big black holes. So yes, there have been quite a lot of measurements of gravitational waves. What is the next level? Well, first thing is they're going to make LIGO better. That's one of the first things that they're going to do. But there's going to be a space mission funded by ESA to build such a detector in space. It's going to be called LISA. And there's a lot of work getting ready. That'll be launched in the 2034, 2035, so, you know, in 25 years' time, no, in 15 years' time. But there's also the discussion, one of the interesting things is other countries are beginning to build their own detectors. So the Japanese have a detector called Kagura, which is going to be working soon. The Indians are thinking of investing in such a machine. So that's the other beauty. You start having more of these telescopes in some sense. So you get better and better measurements of each event. So that's what's happening over the next 20 years.
Can gravitational waves also be used to detect the quasars when the black holes erupt gases?
In principle, yes, but in practice, it's too weak. It's not strong enough. Quasars aren't strong enough. So you need bigger objects. You need either neutron stars or you need black holes.
But wouldn't the ejection alter?
Not strong enough. Really good question. For a while, people tried to come up with all the ways to look for what to look for, what would you might, and that was one of the things, but it's too weak. Back there, right at the back.
Is space and time considered dimension by itself?
Is space and time considered so space and time have a dimensionality. So so you have space, you have time, and then you have 3 spatial dimensions. One of the things that has been discussed over the last 20, 30 years is maybe there are more dimensions to space. Instead of 3, maybe there are 10, maybe there are 26. And so the space and time that we would see now would be just a small part of the full dimensionality of space-time.
Thank you.
You're welcome.
You said that in the future we will see black holes. What we will see, what is expected?
Okay, really good question. So, do you remember Interstellar?
Yes.
You remember Interstellar, right? Do you remember there was this image, which is I'm going to try and do with my hands, okay? So, it looks like this. There's this dark thing, okay? And then around this dark thing, there's kind of a light ring that does that. Do you remember that? Yeah. Right? What you expect to see is that. You expect to see is this ring of light, and then this dark bit in the middle, which is the shadow, which is kind of almost the surface of the black hole. That's what we want to try and see. We want to try and look for this. And this is the thing that the Event Horizon Telescope will see. It's called the shadow.
Okay, thank you.
You're welcome. Back there.
I'm going to speak in Spanish.
Okay, wait a minute. Let me get my machine.
Okay. ¿Hay alguna razón por la que África sea un punto estratégico de observación?
Fantastic question. Okay, so you want to build these telescopes in places which are quiet, right? You want to build these telescopes away from cities or, populations. And so you want to go to deserts. That's the first thing. The second thing is you want to go to places where the air is dry, so you don't have a lot of water vapor, which will make it difficult for you to make these measurements, okay? Third, you want, wherever you build it, in whatever country you do this, you want them to spend money, okay? And so what you have is that South Africa saw this as an opportunity to develop engineers and astronomers and technology. And so they decided to invest money in this. Not only that, there's investment from other countries, and so this is a good way of investing in Africa directly to develop this, this machine. The same thing in Australia. Australia, they have this desert on the west coast, and the problem with the Australian desert is Australia is so big that getting to the desert is very difficult. It's very difficult to get there. It's a lot of driving or a lot of flying. While the African desert, which is the South African desert, which is the Karoo, it's much easier. But those are the main reasons. It's isolated, it's dry, and the countries are willing to invest money in it.
Thank you.
You're welcome.
Pero si ponemos las cosas en el hemisferio sur, veremos el hemisferio sur y no el hemisferio norte.
That is always the problem. That is always the problem. In fact...
Porque los rusos tienen Siberia, pero claro, esos no juegan.
It's true, but we really don't know where to build it in the northern hemisphere.
In Canada, what about Canada or Alaska?
Too humid.
Humid? All right.
Too much water. Although they're building a different type of radio telescope near Vancouver, but it wouldn't work. It's not like the... you can do some of the things of the SKA, but it's a much smaller scale.
Bueno, otra cosa. If those gravitational waves are waves, they are supposed to behave as any other wave.
Say that again?
If those gravitational waves are waves, they are supposed to behave as any other wave.
Yes.
So you may be able to harness all those waves with lenses and things like that, to use them, as you do with the radio frequency emission. Is right now technology developing to harness those waves in that way?
Well, you can think of these gravitational wave observatories as exactly that. So for example, for radio waves, one of the ways of measuring radio waves is using interferometers. That's one type of telescope. So you can think of LIGO as such a type of telescope. So it is already a telescope in that sense.
If some of those black holes are so big, why haven't we seen them yet?
That's a really good question. And not only that, we were completely surprised when we found out that the black holes could be so big. For many years, we thought that black holes had to be smaller, had to be a few times bigger than the sun. But the black holes that we saw are 20, 30, 40 times bigger than the sun. It's a mystery.
Si les parece, vamos a dejarlo aquí. Espero que hayan disfrutado de la fantástica charla que nos ha dado Pedro. Y espero volver a verles en la próxima actividad de astronomía, que será el próximo 14 de febrero. Un tema sobre Marte. Muchas gracias a todos y les pido, por favor, un fuerte aplauso para Pedro. Gracias.